All right, today we're tackling a really cool challenge. How do you take these huge, kind of mind-bending ideas from physics, things like forces and energy, and make them actually click for a 9-year-old? Well, the secret isn't just about dumbing things down. No, it's about making it real, something they can touch. Let's dive in.
And yeah, that's really the big question, isn't it? I mean, you've got fourth graders who are by nature very concrete thinkers. They learn by doing, by seeing, by touching. But physics, it's just full of these abstract ideas. So how on earth do you build that bridge without leaning on a bunch of complicated math they haven't learned yet? And this really gets to the heart of the problem. Concepts like force or waves or how energy moves from one place to another, they're all invisible. They're abstract. You can't just hand a kid a textbook and expect them to memorize it. They need to get their hands on it, to see it in action, to really feel it before they can understand it. Now, you know what's really interesting? The official guidelines, they actually get this. This quote from the fourth grade standards pretty much says it all. It sets a really clear boundary. The goal is not calculation, it's understanding. We're focusing on the what and the why, the big ideas, not the nitty-gritty math. So how do we pull that off? Well, the answer is you totally transform the classroom. Seriously, forget about old school lectures. The modern way of doing this turns students from just passive listeners into active, hands-on investigators. The whole classroom basically becomes a laboratory where curiosity is the most important subject on the schedule. And this is the roadmap for that whole journey. It's a simple 5-step process. First, you engage their curiosity with something really cool. Then, you let them explore it for themselves. After that, everyone comes together to explain what they found. Then, they elaborate on it by trying to apply that new idea to a different problem. And finally, you evaluate what they've actually learned. It's this amazing little cycle of discovery. Okay, so let's actually see what this blueprint looks like in action. We're going to follow a student, just a hypothetical fourth grader, as they work their way through 3 core physics concepts, starting with something you and I see every single day. Our first investigation kicks off with a super simple question that, honestly, any kid can get excited about. We all know a toy car rolls down a ramp, right? But what makes it speed up or slow down? This really simple setup becomes a perfect little laboratory for understanding one of the biggest ideas in physics: forces. And get this, look at the toolkit. We're not talking about some fancy, expensive lab equipment here. It's just a toy car, a ramp, a meter stick, and a few different surfaces to test. This is science that's super accessible, it's tangible, and it's just plain fun. The students actually get to be the scientists. So as they're running their experiments, they start collecting real data. They're not just messing around, they are observing, they are measuring, they are recording, they're turning what they're doing into actual evidence. And pretty quickly, they see a pattern emerge. The car goes way farther on the smooth tile and stops super short on the rough sandpaper. And that data, that's the key that unlocks the whole thing. And this is where that explain phase really comes to life. Using the data they just collected, the teacher can introduce these big ideas. The car slowing down is a perfect real-world example of an unbalanced force. In this case, it's friction, and it's changing the car's motion. Suddenly, unbalanced force isn't just a term in a textbook, it's something they just saw and measured themselves. Okay, so we've gone from forces you can pretty much see and feel to forces you, well, can't. After they've explored direct pushes and pulls, it's time to introduce a little bit of magic, forces that can act from a distance. Yep, we're talking about the invisible, amazing world of magnets. Now, the definition here seems simple enough, but for a kid, the experience is just so powerful. They get to play around and actually feel how magnets can pull a paperclip without even touching it, or push another magnet away. It builds directly on what they just learned about pushes and pulls, but it adds this whole fascinating new layer of acting across a distance. All right, for our final stop, we're going to tackle one of the trickiest ideas out there: energy transfer. I mean, how do you make the concept of a wave, the thing that carries sound or light, visible to a 9-year-old? It's easy. You give them a slinky. So when a student gives one end of the slinky a little push, they can literally watch that ripple travel all the way to the other side. But here's the real mind-blowing part. The slinky itself doesn't actually go anywhere. The little metal coils just move back and forth. But the energy from their push, that travels all the way down. That right there, that's a huge aha moment that makes this abstract idea of energy transfer totally concrete. So the students have done all this cool stuff. They've explored, they've experimented, they've talked about it. But how do we actually know they've learned it? How do we measure this kind of deep conceptual understanding? Well, the answer is you have to completely change how you think about testing. This isn't about some multiple choice quiz on vocabulary words. No. It's about asking the students to think like scientists, to act like scientists, and to argue like scientists. And this, right here, is the secret weapon, the claim, evidence, and reasoning framework. It's so simple but so powerful. First, students make a claim, a clear answer to the question. Then, they have to back it up with evidence, and not just any evidence, their own data that they collected. And then, the most important part, they provide the reasoning. That's the scientific idea that connects their claim to their evidence. They aren't just spitting back facts, they're actually building knowledge. So, when you step back and look at all this, you might ask, why does this matter so much? Because what's really being taught here is so much bigger than the definition of friction or how a magnet works. It's all about building a foundation for a completely different way of thinking. Because, the number one goal here isn't necessarily to churn out a classroom full of future physicists, although, hey, that would be pretty cool. The real goal is to cultivate a mindset, a way of looking at the world with curiosity and with logic. No, it's about building these skills, the ones that stick with you for life. It's so much more than just science class. It's about learning how to stay curious, how to think critically, how to use evidence to make sense of the world around you, and how to tackle problems in a creative way. I mean, these are skills they're going to use in every part of their lives.
And that really brings us to one last big thought. If we can use this hands-on, evidence-based, discovery-driven approach to make something as abstract as physics not just understandable but genuinely exciting for a 9-year-old, just imagine, what else could we learn this way?